In the last lecture, I brought up this idea of a cosmological redshift, that as the universe expands, radiation itself gets stretched out, as you can see on the balloon there, starting with shorter wavelengths and ending up with longer wavelengths. The reason this is so important is that, like any theory, when you come up with a theory in science, you have to put it out there that there are going to be observations that back up your theory. If I'm right, then we should observe A, B, and C. So one of the things predicted by the Big Bang Theory was that there should be this sort of leftover radiation from the Big Bang era. Now, it will be very stretched out and sort of weakened in intensity over billions and billions of years. But for decades, nobody had found that until these two men found it really by chance, which is a very fascinating story. Penzias and Wilson are working, they're scientists, but they're working for the telephone company. And they're working on this radio dish. And the problem they're having with this big radio dish in New Jersey is that they're getting sort of a background hiss. And they go through the usual suspects. They probably check the wiring and stuff like that. And they point the dish in different directions. But no matter where they point it, they always get this background hiss. They can't figure it out. They finally climb up in the dish and they discover some pigeons living in the dish, and they shoo them away and clean up the droppings. And I just think it's funny to imagine these two men on the verge of making one of the great scientific discoveries of the 20th century, on the cusp of winning the Nobel Prize, and they're cleaning out pigeon dung from the receiver. But that doesn't work. They actually eventually take a rifle to the pigeons. But anyway, poor pigeons didn't have anything to do with it. Instead, what they eventually did was go down the road to Princeton University, where it just so happens a professor was putting together a team to search for this microwave background that should be there. And these two men walk in the door and say, "Hey, can you help us? We have this signal. We're not sure what it is." And the professor says, "Congratulations, you've just proven the Big Bang Theory. Now go get your Nobel Prize," which they did. So, just sort of by sheer luck, these gentlemen won the Nobel Prize because that was the leftover radiation from a time period not exactly at the Big Bang, but a little bit after the Big Bang. Remember, in cosmological terms, 380,000 years is very, very, very early in the history of the universe. But before that, it was really too dense for radiation to fly freely. And so the universe is opaque earlier than 380,000 years. So that's the earliest point where radiation was free to fly, and that's as far back, in other words, as we can really look. And here's what happened, though, to that radiation. As predicted, it started out with these high-energy gamma rays in that first second after the Big Bang, but over billions and billions of years, the intensity has dropped, and the wavelengths have spread out due to this severe cosmological redshift, to where today they are in the microwave part of the spectrum, which is why we call it the cosmic microwave background. It's actually so weak, it's the same radiation you would get from an object at only 2.7 Kelvin. So if you put an object in a room and you cool it down to almost as cold as possible, negative 400 something degrees Fahrenheit, the radiation you would get off from that would be equivalent to the radiation we see everywhere in the sky. But that's huge, because that was what was predicted by the Big Bang Theory. There was still one problem. Everywhere they looked, it seemed that the radiation was the same. Why is that a problem? Because that would indicate a smooth early universe. But that's not what we see today. Okay? It would almost be like with the raisin bread analogy I gave the other day. If you put the raisins and you purposely space them out in the dough and you bake the raisin bread, and you come to find out after you bake it that the raisins have all clumped together. It doesn't make sense. The baby picture didn't match the adult current universe. So many years went by before we had the technology to actually look at this radiation more closely. And then in 1989, we launched the COBE satellite, the Cosmic Background Explorer. And this satellite was able to measure the background radiation with much better precision than they could in the 1960s. And here's what they saw. There it is, a baby picture of the universe. This is before stars or galaxies even existed. The red areas indicate the high density areas with lots of matter and energy. And that is what became the galaxy clusters, the strands that we see today. And of course, that means the blue areas, the low energy areas, became the voids that we see. So the baby picture matches what the universe looks like today. We have since then measured it even more precisely with the WMAP satellite, which was launched in the early 2000s, and the Wilkinson Microwave Anisotropy Probe. And here are the results from it, and they did a nice little 3D rendering here. Everywhere we look in the sky then, that cosmic microwave background has very, very tiny fluctuations, but that was enough to create the universe that we live in today. Thanks for listening.